So I, anyway, I'm not going to talk about myself, but when I found out about Guy in late 2016, it totally changed my life. And I said, I need to talk with Professor McPherson. We started communicating. I invited him up to California to speak at the Sierra Club dinners, which I'm program chair of. And he has just absolutely changed the lives of so many people around us. And without further ado, since we're a little bit over time, and just so folks know, we're at the end of this next hour, and please spill into the next hour. Guy and Ye, I've cut into your time a little bit. Sorry for that. But you feel free to take the time that you need, because here's what we're doing. In addition to close to 100 2-minute presentations today over the course of the press conference, we're dropping in a single 1-hour chunk starting now, which is Professor Guy McPherson and Ye Tao, who are dealing with, I put it in the following terms, and there's a lot of stuff that's urgent right now, okay? I talk about the hypothetical dysfunctional family where, the teenage daughter is on drugs, the boy has run away from home, and this and that, and the mom's depressed, and the dad's alcoholic. And the house is on fire. So who does the first call go to? To the kid's truant officer, to the dad's AA sponsor, to the mom's drug dealer? How about 911? Maybe let's kind of put out the fire first. So Professor Guy McPherson is 911. He is the 911 call, and it's up to humanity to answer that call. Dr. Ye Tao at Harvard has answered the call. So you're going to hear about the problem, you're going to hear about the solution, but you're not going to hear more from me because I'm going to turn it over to our experts. And Guy, you give me the green light when you want me to screen share and share that video. Professor Guy McPherson, we love you. Welcome home. We need you. And we need you, Dr. Ye Tao. We need you both. And please take it away, Guy.
Thank you, Jamin. Thanks to James for the very heartfelt comments. Before I got started here, I want to point out 2 errors, and then I'd like you to run that video that I sent in advance. There's 2 errors. Most of the way through, I incorrectly say migration when I meant to say mitigation. And I think most people will be able to pick that up because I'm actually talking about mitigating. And then secondly, an error of omission. I failed to point out that one of the most conservative scientific bodies in the history of the planet, the Intergovernmental Panel on Climate Change, released their report in September of 2019, claiming that climate change is now irreversible because of the overheated oceans. So a couple of errors, one of commission, one of omission, and feel free to run that tape. Thank you, Jamin. Thank you for everybody involved here tonight.
Absolutely. Thank you, Guy. All right, this recording goes for 22 minutes, something like that. So we're just going to sit back and watch and it's all being recorded as well. And then we'll turn it back over to Guy for comments. And then Guy will introduce one of my greatest heroes in life, Dr. Ye Tao at Harvard. All right. Without further ado, I'm going to screen share, and please enjoy Professor Guy McPherson.
Thanks to Jamin Shively for the invitation to speak to the press conference today. I am going to set up Dr. Ye Tao's presentation by pointing out the dire nature of the predicament in which we find ourselves. So I'm going to describe the greenhouse effect and the idea of self-reinforcing feedback loops and the notion that it might actually be too late. And then, as every previous generation of humans has done, at least for the last few thousand years, I'm going to rely upon a future generation to fix the errors of my generation. That's the job of Dr. Tao, following me. All right, so to start, we've known about the mechanism underlying planetary warming since John Tyndall's 1863 lecture, which he went on to publish in his 1872 book, using these words. Quote, thus the atmosphere admits of the entrance of the solar heat, but checks its exit, and the result is a tendency to accumulate heat at the surface of the planet. That's how the greenhouse gases work. They trap heat, much like a blanket that you put on at night when you need to keep a little warmer. You need to trap that heat in. Actually, you could argue that 25 years before that book was published, intelligent people understood what was going on with warming, albeit not necessarily at the planetary level. This is from a presentation delivered by George Perkins Marsh, United States ambassador and naturalist, and it was delivered before the Agricultural Society of Rutland County on September 30th, 1847. He included these words: "The mean temperature of London is a degree or two higher than that of the surrounding country, and Pallas believed that the climate of even so thinly a peopled country as Russia was sensibly modified by similar causes," end quote. And by Pallas, he's referring to a German scientist, a contemporary scientist at that time. So, although Marsh doesn't necessarily understand the level of planetary warming, he is hinting at the notion of warming at a relatively large level, a regional level. Fast forward to April of 1896, with the first peer-reviewed article I know about appearing in Philosophical Magazine and Journal of Science, authored by Svante Arrhenius, in which he predicted, after describing the greenhouse effect, a 1 degree Celsius global average temperature increase by the year 2000. He missed it by 0.24 degrees. The global average temperature at that time was 0.76 degrees higher than the 1750 baseline. We use the 1750 baseline as the beginning of the Industrial Revolution, therefore is the year which we compare contemporary global average temperatures to. So Svante Arrhenius described a 1 degree Celsius global average temperature increase above the 1750 baseline, and in the year 2000 that temperature was actually 0.76 degrees above the 1750 baseline. Not bad, more than 100 years in advance. And wise of him to make a prediction that he was certain he wouldn't be around to see whether it was wrong or not. Moving to February of 1938 and the peer-reviewed journal Quarterly Review of the Royal Meteorological Society, we have Guy Callender describing in this simple graph the increase in temperature over time. You'll notice that he uses 1880 as his starting point, and you can see that there's variation over time, but there's a significant increase in global average temperature from 1880 to when he published the paper in 1938. Enter Humble Oil, which went on to become ExxonMobil, and in an advertisement in Life magazine on February 2nd, 1962, Humble Oil brags, "Each day, Humble supplies enough energy to melt 7 million tons of glacier." Now, of course, we recognize that's not such a swift thing. But in 1862, it seemed like a good idea to use fossil fuels, most notably oil and coal, to heat ourselves. And the comparison to melting ice is something that people can identify with. Let's move now to 1969 and the presidential administration of Richard Nixon in the United States. This from a memorandum he wrote to John Ehrlichman, a senior member of his administration. He's describing the carbon dioxide problem in the atmosphere. And he says carbon dioxide very clearly is a problem. He puts the emphasis by underlining is a problem, and perhaps most particularly is one that can seize the imagination of persons normally indifferent to projects of apocalyptic change. His language, apocalyptic change, that we face in the future. The process is a simple one, and then he goes on to describe the relatively simple process of planetary heating through greenhouse gases. And he writes, "It is entirely possible that there will be countervailing effects. For example, an increase of dust in the atmosphere would tend to lower temperatures and might offset the CO2 effect." So he recognized and wrote about the aerosol masking effect, global dimming. And I'm not going to spend any time on that particular topic, but
it's clear that Richard Nixon knew about the aerosol masking effect in 1969. It's something that very few people know about. I've never heard a leading politician, a politician of any kind, talk about the aerosol masking effect within the last 40 years. Within my lifetime, I haven't heard that ever happen. In the 1980s, Al Gore, Carl Sagan, and James Hansen testified to the US Congress describing where we were headed. And NOAA also in the 1980s, specifically in 1985 and forward, NOAA reports that the last global average temperature for any month was in February 1985. Since then, the global average temperature on a monthly basis has increased with every month. And you can see with the figure here that the temperature just keeps rising. No matter how many times people talk about it and give these warnings, the temperature just keeps going up. Isn't that interesting? My last report from the 1980s comes from the Associated Press on June 29th, 1989, and this is in the Associated Press, so it's reported in every significant newspaper in the United States. Quoting from the article, Noel Brown, director of the New York office of the UN Environment Program, said governments have a 10-year window of opportunity to solve the greenhouse effect before it goes beyond human control. That was 1989. United Nations Advisory Group on Greenhouse Gases, about 16 months later, in October 1990, writes, beyond 1 degree C may elicit rapid, unpredictable, and nonlinear responses that could lead to extensive ecosystem damage, thereby recognizing self-reinforcing feedback loops, and also recognizing the importance of ecosystem function in maintenance of habitat for human animals and other organisms on Earth. Moving to 2006, Time magazine says on the cover, be worried, be very worried. That's April 3rd, 2006, with a special report on global warming from Time magazine. Finally, in 2014, just 54 years after bragging about how they could melt glaciers, ExxonMobil, specifically the CEO of ExxonMobil, says climate change is a top priority. This in Natural Gas Intelligence on May 28th, 2014. So finally catching up a little late to the party for making significant changes. Speaking of those self-reinforcing feedback loops, David Spratt, climate science speaker and writer, said in a presentation in October 2014 that we probably triggered those self-reinforcing feedback loops at or slightly below 0.5 degree Celsius above the 1750 baseline. 1750 baseline is about 13.5 degrees global average temperature, and he indicated that at about 14 degrees, which is long before anybody watching this presentation was born, is when we trigger those self-reinforcing feedback loops. So that's kind of a bummer. The warnings keep coming. The 10th of September 2018, Antonio Guterres, Secretary General of the United Nations, said, quote, world has until 2020 to change course in order to avoid runaway climate change. Well, we're past until 2020. We're well into 2020 at this point, and there's been no significant measure conducted to arrest runaway climate change. And then just a couple of weeks later, approximately a month later, the United Nations Intergovernmental Panel on Climate Change concludes, quote, with clear benefits to people and natural ecosystems, limiting global warming to 1.5 degrees C compared to 2 degrees C could go hand in hand with ensuring a more sustainable and equitable society. Yes, I'm sure that's true. Had we been able to arrest global average temperature at 1.5 degrees, it would have made a difference in terms of ecosystem response and human response. After all, when we were at slightly more than 1.7 degrees C above the 1750 baseline, a paper by James Hansen and colleagues indicates that we were at the warmest temperature ever experienced by Homo sapiens in our history on Earth. I want to switch topics a little bit here and talk about the rate of global average temperature rise as it relates to environmental change and how that affects vertebrates and mammals. After all, as vertebrate mammals, humans should be concerned about the rate of change and how it impacts vertebrates and mammals. So, a peer-reviewed paper by Quintero and Wiens, published in Ecology Letters, with a focus on vertebrate species, published June 26, 2013, and using the Intergovernmental Panel on Climate Change projection of temperature rise to the year 2100, Quintero and Wiens conclude in their paper, quote, "Our results are striking. Matching projected changes for 2100 would require rates of niche evolution that are more than 10,000 times faster than rates typically observed among species. More than 10,000 times faster than the rate of change that matches the projected rate of change by the IPCC, which is very, very slow." Again, they're focusing on vertebrate species. Davis and colleagues, publishing in the Proceedings of the National Academy of Sciences on October 30th, 2018, with a focus on mammals now, concludes, quote, "We use a birth-death tree framework to show that even if extinction rates slow to pre-anthropogenic background levels, recovery will likely take millions of years." Again, that focuses on mammals, and we know of no way, besides the one that is following this presentation, to return extinction rates to pre-anthropogenic background levels. We're in the midst of a mass extinction event, reported in many popular magazines and books going back a decade or more, and appearing for the first time in the peer-reviewed literature in June of 2015. As an indication of how conservative the peer-reviewed literature is, a paper by conservation biologist Gerardo Ceballos in Science Advances, titled "Accelerated Modern Human-Induced Species Losses Entering the Sixth Mass Extinction." The title indicates, as does the paper, that we are just now entering the sixth mass extinction, even though I would argue that we had known for at least 5 years, and probably at least 10 years as of 2015, that we were in the midst of a mass extinction event. Conservation biologist Gerardo Ceballos, again, with colleagues, again, this time in July 2017, in the Proceedings of the National Academy of Sciences, another peer-reviewed journal. The title is "Biological Annihilation." You don't see that in the title of a peer-reviewed journal very often. Biological annihilation via the ongoing sixth mass extinction signaled by vertebrate population losses and declines. And finally, in the most recent paper by Ceballos and colleagues, this one co-authored by conservation biologist Paul Ehrlich at Stanford and by Peter Raven of the Missouri Botanical Garden, and published in, again, the peer-reviewed Proceedings of the National Academy of Sciences. The title of the paper is "Vertebrates on the Brink as Indicators of Biological Annihilation." Again, that phrase, and the sixth mass extinction. And the quote from the paper is telling: "The ongoing sixth mass extinction may be the most serious environmental threat to the persistence of civilization because it is irreversible and accelerating." And now we know that because of the aerosol masking effect or global dimming, if we lose civilization, the global average temperature rises very quickly, far too fast for not only other vertebrate mammals to keep up, but ours as well. After all, we're at the warmest temperature experienced by Homo sapiens in our history right now, according to a paper by James Hansen and colleagues published in 2017. To change course again just a little bit, I want to point out that we are in the midst of a mass extinction event. According to the United Nations Environment Program, in a report published August of 2010, in other words, more than 10 years ago, we were driving an estimated 150 to 200 species to extinction every day. Every day. That's what's going on right now as a result of human activities, and including the abrupt global average rise in temperature that has taken the situation out of human hands at this point. This could very well lead to the extinction of all life on Earth, as pointed out in a paper by Strona and Bradshaw, published November 13th, 2018 in Scientific Reports, with the title "Co-extinctions Annihilate Planetary Life During Extreme Environmental Change." And what they mean by extreme environmental change is environmental change including global warming that occurs faster than species can evolve through natural selection in response. In an interview conducted the following day, November 14th, 2018, the lead author Strona says, "Our paper demonstrates that even the most tolerant species ultimately succumb to extinction when the less tolerant species on which they depend disappear. Thus the term co-extinctions. When we depend upon a species or many other species for our own survival, and those species go extinct, we don't have options anymore. We go extinct as well." That's the idea of co-extinctions. I want to back up a little bit and talk about the idea of habitat. I already indicated that humans are vertebrate mammals, and as with other vertebrate mammals, we have habitat needs. We demand a certain set of materials so that we can continue to survive. The best short definition I can find of habitat is, quote, "the resources and conditions present in an area that produce occupancy, including survival and reproduction, by a given organism." That by Linnea Hall and colleagues in Wildlife Society Bulletin in 1997. Speaking of habitat, let's turn to a major synthetic paper published by the European Strategy and Policy Analysis System in 2019. And here's the signature quote from that major synthetic work. Quote, "An increase of 1.5 degrees, again that's 1.5 degrees above the 1750 baseline. An increase of 1.5 degrees is the maximum the planet can tolerate. Should temperatures increase further, we will face even more droughts, floods, extreme heat, and poverty, and at worst the extinction of humankind altogether." End quote. And at the time, we were well above 1.5 degrees C, above the 1750 baseline. Next up is a potential project that might actually serve to cool or stabilize the current planetary temperature. This is called geoengineering, and the idea that geoengineering could come to the rescue was discussed by the United States National Academy of Sciences in a major report published February 20th, 2015. So about 5.5 years ago, and they found that geoengineering is not a viable solution to deal with the climate crisis. European transdisciplinary assessment of climate engineering, in other words, a large-scale European assessment, addressed the same topic with a report that came out July 16th, 2015, and reached the same conclusion. It's too little, too late. Extinction awaits for humans and therefore for all life on Earth. With that, and with the notion that every generation, at least for the last few thousand years, every generation of Homo sapiens depends upon future generations to fix all that ails us, I'm going to turn it over to one of the people I respect most in the world of climate science and engineering. Dr. Ye Tao from the Rowland Institute at Harvard University has what I believe to be the most likely potential solution for the dire predicament we find ourselves in with respect to overheating the planet. Thank you very much. I look forward to continued interactions with everybody in this group.
Beautiful guy. Oh my goodness. Just incredible. I mean, here's the thing. I just got to put this out there because not everybody knows this, and Guy certainly doesn't go around advertising it. But not only is he just absolutely AAA plus scientist, he won the highest distinguished teaching awards that the University of Arizona gives, including like I mean, just like spanning multiple different, departments. I mean, his teaching is just overwhelming. And it's changed my life. And let it change yours, and let it change the lives of everyone around you as quickly as possible, because we need to hear the 911 call. And the head of the planetary fire department is Dr. Yatow at Harvard, one of my major heroes in life. And I'm going to let Guy really give the introduction to Ye. And welcome, brother. Welcome back. Welcome home. Love you both. Love you all. Guy, take it away.
Thank you. Dr. Tao began a conversation with me about a year and a quarter ago, as I recall. Subsequently came to the rental home where I was living in Pleasantville, New York, about an hour north of Manhattan. And we had a conversation for a couple or 3 hours. And subsequently, Dr. Tao has, beyond the work that he is required to do to earn a paycheck, has been seeking out potential geoengineering solutions to the overheating of the planet. And I think that his is the only approach that I know about anyway that can cool the planetary temperature. So I have great respect for this man. Please give him your focused attention.
Well, thank you for such a generous introduction. I hope I can live up to the standards and expectations. So I just had a really long day, like 10 hours of meetings back to back. So I hope my brain still works. So please feel free to send in questions and maybe even interrupt if anything is unclear. So let me try if I can share screens.
Oh yeah. Let me get on top of that. 1 second, and you're good to go. Thank you.
All right, let's see. All right, everybody sees the slides?
Yes, we do. Yeah.
All right. So at the risk of repeating myself, because I'm sure many of you have already seen like previous presentations, I would just give a quick introduction to my institute where I work. So I work at the Rowland Institute, which is right by the Charles River, next to the Longfellow Bridge, if you ever come by Boston, Cambridge area. So the building has a historical connection with the late Dr. Edwin H. Land, the founder of Polaroid cameras. So he basically established the Institute as a retirement hobby shop to support crazy science and especially instrumentation. He also was the guy behind the construction of the Harvard Science Center. So he's very much involved in education and of the young. So we like to joke that students take classes there and then they come to us to get trained doing experiments. So right now we hire about between 0 to 2 fellows like myself per year. For 5 years, we are tasked with developing any crazy idea that we think are important to investigate. And we're also allowed to change direction mid-course, which is not usual these days, because usually you have to, answer to the funder and write a quarterly report. So that really constrains science. So I think the Rowland Institute may be one of the last bastions of true scientific investigation. So at the Institute, we do a range of topics across length scales from the very molecular up to previously to like the meter scale. And we also investigate topics that involve understanding entities and systems, either static in time or interacting through time. And sometimes it's very complex. For example, the interaction between microbes and the host, for example, in different kind of bees in their guts, and the toxicity effect of, say, pesticides, and how those 3 things interact together. But since roughly 2 or let's say like 2.5, 3 years, due to the teaching by Guy, I've become really concerned and interested at the same time about a field that I term civilizational habitat engineering. And that's really something that encompasses all length scales, as I have discovered. And it encompasses many different dynamical systems as well. So it, in addition to being something that I feel personally, something a responsible scientist needs to be looking into, it also has been quite rewarding, actually, intellectually. So in my lab, before I got into climate science and engineering, I've always taken a target-driven approach. If you have some like grand vision in mind, generally drives you to make, say, the tools in order to make some, this sort of discovery. And oftentimes we find that existing technology or commercially available product simply isn't sufficient for you to accomplish your mission. So we are forced, in order to accomplish our mission, to develop new tools, new instrumentation. And in the process of doing that, we often find new science that just pop up or wasn't discoverable before such new tools are invented. So this sort of target-driven research has really proven quite fruitful in my previous career. And just for like background, we used to be looking into, we tried to build a microscope that takes MRI images. Many people probably have gone to doctors and get MRI images of their body parts. We wanted to do that with a higher resolution, but of small entities, for example, of a virus particle like COVID, let's say. And if we can really have atomic resolution images of these entities in 3 dimensions, it will be much easier, say, to design drugs or agents against them. So having such imaging capability would have very much a lot of application in material science and in medicine in general. So with that sort of grand vision, we were able to do a lot of interesting science, including a project that we're still working on a little bit. How do you subtractively machine, basically remove material and make different shapes with very high spatial precision. So in this example, we're able to subtract lines and little dots from a gold surface, but with a very high depth precision. If we look at the height axis, we're looking at a few nanometers. So for comparison, 0.2 nanometers is roughly the thickness of a single atom. So in these cases, in the faintest line, we're basically removing 1 layer of atom. So, but that's really on the far extreme compared to climate change. So at a certain point, I said, wait a minute, the world is literally on fire everywhere around the globe. So what's the point of developing, say, such an imaging tool if there's not even the next generation of grad students or clinicians to use them? So rather than focusing on the original target, which was of high personal scientific interest to me, it's clear, like promoting or maintaining habitat for a human was a much more urgent task. And like there are many equally urgent tasks, including educating, say, the next generation of scientists, engineers who will be at the forefront of the fight, constructing different solutions. So today I will mostly tell you about how we are thinking about the engineering for habitability of planet Earth, and a little bit about how I'm trying to incorporate both the solution development and educational component together. So you probably have noticed that I like to do these 2-dimensional plots because I find it's quite illuminating. It teases apart many parameters and put things into perspective. So here, I'm plotting examples of different threats that we talk about in the news, and really consider whether they are indeed urgent or whether we should focus our attention on these threats. So on the x-axis, I have something I call the urgency. So if it's on the extreme right, it's probably something that's already happening. If it's something on the left side, then it's something we need to worry about a century or a millennium from now. So the first up is sea level rise. That's probably used before this year or the last year by the corporate media as the most, prominent threat associated with climate change. But if one really looks at peer-reviewed literature, it's quite clear that we have pretty good understanding of the rate at which this will happen. There's probably like an error uncertainty of a factor of 2, but even in the worst case scenarios, we're looking at the sub-trillion-dollar damage in the foreseeable century. So even compared to COVID, that's a manageable risk. Certainly not something close to being able to collapse civilizations. Something that's talked less compared to sea level rise is ocean acidification. It's on a similar timescale, perhaps even later, on the order of 8 years from now, you will start to be seeing extreme pH fluctuations that can affect some communities of organisms, but it's still on the order of a century from now. However, the entire ocean would be affected pretty much, of course, to various degrees, but the ocean is a 3-dimensional object in contrast, say, to the coastline. So it's a much larger threat quantitatively. Air pollution, everybody's familiar with, and that had been a problem here in the US and also in Europe. Now is a problem in South Asia and still parts of East Asia. But we have a pretty good understanding of, say, life expectancy reduction from exposure to air pollution. It's really unfortunate for the people impacted, but and has significant health effects, but it's not something that will collapse civilizations either. Same thing with ocean plastics, despite the visibility, has yet to demonstrate measurable health effect on humans. And the biggest problem that we have kept ignoring are thermal extremes driven by the accumulation of excess heat in the Earth's atmosphere and oceans. And this excess heat drives a range of downstream problems, ranging from epidemics to pests like locust outbreaks, and eventually, and pretty soon, food production reductions, and eventually collapse if demand is significantly underfulfilled. So after this analysis, it became clear to us that we really need to be focusing on the most urgent and the most significant threat. That's thermal extremes. And that's how Project MEER Reflection has been designed around. So I'll go for today. Let's have a quick discussion of exactly how urgent is this crisis. And I'm sure many people here would agree that renewable energy by themselves are not sufficient. So the thought that just buying electric cars and moving the economy to renewables will solve the problem is a myth. And it's an important message that we need to get across to policymakers. And then we'll be ready to talk about the solutions framework and really first get overheating under control, and then optionally consider dealing with greenhouse gases. The rationale for such a sequence will become clear after next slides. So as a material scientist and physical scientist, we like to think about phase diagram. So for example, at what temperature is ice stable? It's below 0 degrees Celsius and at a certain external pressure. So we can also conceptualize, say, the ecosystem or a stable ecosystem on Earth as a phase of organic matter. And we can ask the question, under what physical condition, external physical conditions, do we have a stable ecosystem? And the answer to that can be found by going to peer-reviewed literature on CO2 requirements by plant in order to sustain photosynthesis, and looking at carbon dioxide tolerance for animals. And on the thermal axis, we can also, Guy also mentioned these PNAS papers that really makes it clear that we shouldn't venture anywhere close to 3 degrees Celsius relative to pre-industrial levels for the stability of ecosystems. So the significance of this sort of analysis when we co-plot the trajectory of the Earth, the conditions on Earth as a function of time, is clear. Basically, we are very safe on the CO2 axis. We will not get actually close within the foreseeable future. However, we're already crossing potential boundaries on the temperature axis. So if we simplify it, most people like to think in terms of time into the future. It's equivalent to saying that we are very near hitting at 100 miles an hour a wall that defines the biological thermal tolerance in the next decade or two. And incidentally, even if we were to burn all the fossil fuel reserve on planet Earth, the intrinsic CO2-induced acidity will still not manifest. So the only reason why we ever are focusing on CO2 is because of its indirect effect on the temperature, but not due to the intrinsic chemical properties. Now we're ready to understand why it's a bad idea to immediately stop all fossil fuel emissions and to blindly pursue a renewable transition. As Guy pointed out, co-emitted organic, volatile organic compounds, nitrogen oxides, and ozone drive the formation of aerosols that block significant amount of sunlight from ever reaching the Earth's surface. The net result is a cooling of the planet, and averaged over the heterogeneity of the Earth, we have roughly about 1.6 watt per meter squared, based on this particular simulation study. But very recently, a review paper came out looking at all the literature in the past 40 years, and the value that's most likely to be correct is around 1.2 watt per meter squared with some distribution. Now, the question is, if we were to get rid of this aerosol, what's the temperature rise as a result of an additional 1.2 watt shining on every square meter of Earth? That conversion factor can be found in several ways. So I myself am an experimentalist, so I like to look at past data. So Schneider last year looked at the history of the Earth and extracted a conversion factor of roughly 0.8 degrees Celsius per watt per meter squared of warming. And recent review of computational and experimental evidence suggests that we basically have roughly 1 degree of temperature increase per additional watt per meter squared of heating. It's actually a quite convenient number to remember. So the conversion between the forcing and the equilibrium temperature is roughly 1:1. So the implication of these results, according to the most recent consensus review and reports, is that the result of losing the aerosol produced by fossil fuel co-emissions would be like roughly between 1 to 2 degrees Celsius, somewhere in that range. So that's a list of other papers, many of which Guy has repeatedly cited in his talks, that documents this effect. And COVID really has enabled and will continue to enable experimental demonstrations of this particular effect. So here are some direct measurement in the Netherlands. So scientists and people in the weather prediction services continuously monitor how much sunlight strike the Earth's surface. Not only the net amount, which is represented by the combined height of blue and yellow bars, but also whether the sunlight strike along the direction, the line connecting the sun and the Earth, represented by yellow, or whether the photons take some detour after interacting with the aerosol in the sky and then strike the ground, and that's represented by the blue bars. So the dotted line represents the reduction in flight as a consequence of lockdown imposed in Western Europe. And we see that there is a significant change, first of all, in the proportion of total energy arriving and the proportion that's arriving directly without scattering and changing direction. So we can, for people not used to looking at these graphs, there is a contour going up slowly that's basically increasing solar radiation as spring and summer come. So we can, for this analysis, ignore the slow increasing slope, but focus more on the ratio between the yellow and the total height. So it's quite clear in this region, the ratio is roughly 50% at most, but over here we have predominantly yellow, meaning there's very little scattering. So that's effect number one. The second effect is clear when we look at the net amount of sunlight that have arrived as a result of this reduction in, or maybe not a result, but correlating with this reduction in flight departure frequencies. So it turns out that 2020, at least in Netherlands, at this particular station, it's a record in how much sunlight has struck Earth for the past roughly 100 years. And the increase compared to previous years is roughly like 2 watt per meter squared, which is a number that's entirely consistent with the amount of aerosol masking that computation and experimental observation predict. So now we're ready to discuss hypothetical scenarios of how the Earth would react if we were to blindly pursue renewable energies as solutions. If we were to continue business as usual, doing nothing, obviously the trajectory doesn't look great. We'll continue to warm and very likely in the next decade cross threshold leading to catastrophe. If we were to, on the other hand, switch to renewable, let's say solar energy, represented by either solar thermal, the red one, or the more familiar solar photovoltaics, we will be moving along this trajectory. The reason for this cyan arrow going up is because of the loss of anthropogenic aerosols, the effect that we have been discussing. Certainly, there is some error bar as to where the range is, where this particular point will be landing at, but we have a very high confidence that it will be somewhere in that range, most likely above 2 degrees Celsius, above 1750 baseline. If I had to make a bet, I would, put my bet above there. Of course, that increase by this range will not materialize overnight. So it will roughly 50% of that increase will take place within the first 5 to 10 years. And the remaining 50% will probably take place over the next century or two. But even with 50% of that range, we will still most likely go over 2 degrees Celsius, which is beyond catastrophic by all estimates. So now we can understand why just pursuing a renewable energy transition, regardless how quickly we do it, is not going to solve the problem. So to add salt to injury, a very recent paper that the guy pointed out in one of his talks, I think. So people did simulation recently of 2 hypothetical scenarios of future emission. One, we do a very aggressive reduction linearly from now until the end of century and going to net zero. The other is somehow, let's say we magically stop all emissions. Let's see what how the Earth evolves in the future. So in both scenarios, regardless whether we stop slowly or immediately stop, the long-term trend is continued increase in temperature. And that holds for both the temperature trend and also continued sea level rise as a result of losing sea ice and other glaciers and land ice. In this particular simplified model, the authors doesn't seem to have included the aerosol forcing because we do not see the immediate increase, but that's just the particular model components that's incorporated. But nevertheless, even with conservative model not including the effect, the conclusion from the study is that the Earth already has been pushed into the state with a mind of its own, that it will continue to evolve and increase in temperature unless very drastic countermeasures are taken. So now let's talk about what those countermeasures are and what measures can, in principle, be effective. So let's quickly review what controls the climate on planet Earth. Life is able to survive on planet Earth because our atmosphere helps to trap heat. Otherwise, our planet would be at perpetually minus 20 something degrees Celsius below the freezing point. So we basically have energy coming in the form of a shortwave solar radiation and some form of energy out through several different pathways. But for the purpose of this discussion, it's not important to understand exactly how energy go out at different partitioning points. All we need to worry is that in the past, in pre-industrial times, we had a relatively stable climate, basically, alternatively, a relatively constant level of heat or thermal energy trapped in the Earth's atmosphere and oceans as a result of a balance between the rate of energy input versus the total energy outgoing flux. What happened recently as a result of burning of fossil fuel is that we have shut off the outlet, leading to a reduced flux going out. Consequently, we have an increase over time of how much heat, how much thermal energy in the atmosphere. So in order to return to a stable climate, meaning the net amount of heat no longer change in the Earth biosphere and ecosystem, we have 2 options. One option is, like we have been trying, to somehow open that outlet so that more heat, or in the form of long-wave radiation, escape. Alternatively, we can achieve the same balance by reducing how much energy is coming in the first place, converting into heat. So these 2 approaches, basically the only one that we have based on the physics of the situation, has led to 2 families of proposed solutions. On the long wave outlet targeting end, people are calling for reducing greenhouse gas emissions, even cleaning up the atmosphere by filtering away CO2 gases and other gases. These approaches are conceptually 3-dimensional engineering challenges because it entails cleaning up an atmosphere, which is itself a three-dimensional volume, and which is constantly mixing, and also the ocean, where we have already stored a huge amount of carbon dioxide. If we took instead the shortwave targeting solution, it's a much more manageable engineering problem because a very thin reflective surface, such as an aluminum foil from your kitchen, is able to instantaneously send out most of the sunlight striking that area back into space. So in the world of geoengineering, we can conceptually divide or place the various strategies on different locations of this path of energy flow from the sun into the atmosphere, striking ground, re-emitting, maybe hitting some clouds, be trapped, and then eventually going into space. So the discussion we just had essentially means that all solutions targeting greenhouse gas via filtering the atmosphere, regardless of which process they use, whether it's industrial or increasing the rate of natural weathering or relying on very slowly growing trees, are not going to work due to the kinetics of the problem. And the only approaches worth considering are approaches based on reflecting away the shortwave radiation, because they, in principle, can be implemented as a two-dimensional solution, whereas these ones, due to the three-dimensional nature, in practice, the third dimension becomes time. It takes time to filter things, and it's simply not possible from either the kinetics, the time point of view, or the energetic requirement of these processes, which we will not have time to go into today. So our project basically asks the question, is it possible at ground level to reject enough sunlight to have a significant impact? This map plots the level of sunlight hitting the Earth on average during 2018, multiplied by 1 over the albedo, or a factor that describes what fraction of the incoming sunlight is absorbed rather than naturally reflected. So we see the bright spots are subtropical oceans. That's where we have both a lot of sunlight and also a very dark absorbing surface. That's the ocean, which means there's a lot of potential to boost the local reflectivity in order to prevent the conversion of the light into heat, which is then trapped in the ocean. So using the range of numbers here, we basically can have a first order estimate, which shows if we want to balance out 1.5 watt per meter squared of heating, or roughly 1.5 degrees Celsius of warming, we need to cover roughly 1% of the Earth's surface using MEERs in locations with solar radiation that's greater than roughly 200 watt per meter squared, which covers most of the planet. And it's worth mentioning that these numbers are calculated for horizontal MEERs such as these that's lying flat. If we further allow the possibility to angle the MEERs toward the sun, we can achieve higher efficiencies on land. So here is a calculation that shows in the financial terms why targeting the heat using MEERs is a financially viable solution. So we all know that people are proposing carbon tax, but generally the price are tens of dollars to hundreds of dollars. I want to make the claim that using MEERs to target the heat rather than go after filtering the elusive CO2 in the air, we can do this and achieve the same result much cheaper. So 1 ton of CO2 traps roughly, or is heating the Earth at 3 times 10 to the minus 12 watt per meter squared per ton. And we just discussed that MEERs in many parts of the world achieve somewhere between 200 to 300 watt per meter squared of cooling when they are pointed horizontally up. So we can ask the question, averaged to the entire surface of Earth, how much does each meter squared of MEER cool the Earth? So it's simply taking the ratio of the local cooling power by the entire surface of the Earth. And we arrive at a number which is on the same order of magnitude. So we're in business. And to be precise, if we take the ratio of the heating by 1 ton to the cooling by 1 meter squared, we know that roughly 6 meters squared of MEER cancels the heating effect of 1 ton of CO2. And this area of MEER can be sourced commercially at roughly $10 today. Certainly, it's probably not of the high quality that we'd like to make, but at least it shows even at $10 today, there is a profit for the manufacturers. It's important to realize that a project of this magnitude will not be performed by single individuals. So to be successful, we most likely will have to have a coordinated effort by governments. And a colleague just came over. So the energy necessary to produce roughly 10 meter squared of MEER is only about $1 USD, assuming $50 per barrel of oil. So the actual cost, if we were to consider things in energy unit, is somewhere between $1 and $10. Now I want to draw an analogy to help people understand conceptually what MEERs are really. So we know that air conditioners can remove heat from your house to provide a habitable or a more comfortable environment inside. And of course, to do that, you need to supply electricity constantly. So let's say we supply amount of electricity equal to energy amount Q, because it's usually a symbol for heat, flux and heat sometimes. Because the efficiency of cooling is pretty decent compared to, say, heating, which is usually 1-to-1, we actually remove roughly 3 times as much thermal energy from the house to the environment under current external temperature conditions. Now let's ask the same question for the MEER, considering it as a device to remove heat from Earth, which is our common home, out into space. So the amount of energy that's required to make the MEER is roughly the heat that's necessary to melt the glass, and maybe some transportation and installation cost. Let's call that Q prime. It's actually quite easy to calculate based on the insulation values and the demonstrated lifetime of these MEERs of roughly 30 years or more, that over its lifetime, this MEER will reject more than 3,000 times the amount of thermal energy that's used to make it. So by this metric, the MEER is a planetary air conditioning system, which is 1,000 times more energy efficient than your air conditioning. Of course, when you run your air conditioner, there's also CO2 produced as a result of generating that electricity. And this CO2, of course, gets trapped in the atmosphere, and that then leads to 50 times the electrical energy being trapped into our common home as a result of greenhouse effect. Now, we have discussed how it's possible to use MEERs to tackle this most imminent threat. Let's talk about how MEERs can also be used to tackle many other threats, but we'll just discuss the CO2 in ocean acidification effect. But before, it's nice to make another analogy to understand why this can work. So we all use electronics. The most basic devices are light. Anywhere from light to your cell phone, there's different shapes of copper wires and in different sizes. They're nothing but a channel to manipulate the flow of energy in the form of electricity. The same thing can be said of MEERs. They're nothing but devices that manage the flow of light energy. Since wires in different forms are so versatile and enable a wide range of applications in electronics, it should come as no surprise that MEERs can achieve the same versatility. So here is a little busy diagram, but I will go over it slowly. So essentially, we're depicting a scheme through which we can achieve substantial reduction of net CO2 emissions by coupling several processes together in what we call closed loops. In this diagram, there are two important closed loops, one involving predominantly calcium and the other involving carbon. Let's first take a look at the calcium loop. So we start with the compound calcium carbonate, going to calcium oxide, going to calcium hydroxide, going to calcium ions in the ocean, and then coming back to calcium carbonate. Calcium carbonate is the material from which seashells are made of at very high purity of usually above 98%. And calcium oxide, aka quicklime, is an important ingredient in a variety of applications, including concrete production. And calcium ion is certainly important for calcifying organisms that include coral reefs and also these marine bivalves. So now, how do we propose to couple this calcium loop to our human system? So the proposal is that, let's say we increased our bivalve aquaculture, then from this aquaculture, we get nutritional calorie because they're pretty delicious and pretty high in protein. So we get nutritional benefit. After we're done with the organism and its all shells, we can have a dedicated bin to collect them and ship them to a dedicated facility, which uses the heat collected by reflecting mirrors in order to decompose these shells into quicklime, calcium oxide, and stream off gas that's a very pure CO2. This CO2 can be made into liquid fuel using electrocatalytic methods that many labs in the world are actively developing. One of my colleagues at the Rowland Institute developed one such method, and now he's continuing the effort at Rice University. And it's arguably CO2 reduction to fuel one of the most funded and active research alive today. And once we have done that process using electricity generated by solar thermal concentrating solar power, then we can use such carbon neutral fuel to run our mobile transportation devices that include the car, ships, and airplanes, which then release the CO2 into the air to be absorbed by the gigantic surface area of the ocean. And once there, they are ready for another round of carbonate shell formation. So in this way, we utilize calcium, which is intrinsically present in the ocean at quantities far exceeding what's necessary to sustain this closed loop. We use calcium as a pump with the financial incentive of bivalve aquaculture and the potential to capture thermal energy from the hydrolysis of the quicklime to heat our homes to provide financial incentive to keep this pump running, which then in the process leads to a carbon neutral CO2 or liquid fuel based economy. So let's crunch some numbers. So the assumption in this example calculation is that we switched off all land-based agriculture and moved calorie production entirely to a oyster clam protein-based system. And given the 7-8 billion of us, we need 24 exajoule of energy per year. Let's make the assumption that we supply all of that using clam protein. The resulting shell that we get from this amount of clam is sufficient to produce enough calcium oxide to produce basically the same amount of heat that's required to heat everybody's home on planet Earth. And in the process of this solar thermal calcination, the CO2 gas that escapes from the shell also contains enough thermal energy to heat enough water through heat exchanger to provide all the hot water need for the planet. So this scheme, in this hypothetical situation, is able to reduce emissions from land-based agriculture by 6 gigatons, and the fossil fuel used for space and water heating would amount to 9% of current fossil fuel consumption. And of course, roughly half of the current unclosed CO2 emissions, it now becomes carbon neutral CO2 production and then capture via bivalve aquaculture. So the total effect of such a scheme is that we instantaneously make 75% of current CO2 emissions carbon neutral. And if in addition, we assumed if we had such a big solar thermal liming operation, we must have a lot of solar furnaces. So it's quite easy to expand our electricity production to concentrating solar power. Then if we, in addition, produced our electricity that way, then we would have a net greenhouse gas capture potential of 5 gigaton per year. So with that, I'd like to just thank the students and other volunteers that have helped us further develop this scheme, the project MEER Reflection, and also to make our website and other illustrations such as this one, which illustrates the versatility of MEERs in providing stable environment for agriculture, rebuild marine ecosystems, and for generating renewable electricity. We also have methods to tackle the methane release problem based on MEER-enabled technologies, which are still under development. But the most urgent need that we should be promoting is the idea that MEERs can control both local temperature to enable sustainable agriculture and to have a global benefit that radiates out from the specific location of implementation. And with that, I'd like to give it back to Jamin.
Oh my goodness. Yay You just continue to blow me away. I mean, I thought I had seen the best presentation of my life, your last presentation. This one, you just keep outdoing yourself, and you're really in a class all by yourself, because this is exactly the medicine we need. And I'm just so grateful that you're here doing this work. And what it feels like to me is the opportunity for us all to come together, because here in this community, or it's actually a network of networks. We're just one little part of the hyperobject that you can poke and we giggle. But there's this massive hyperobject out there called the network of conversations, the planetary emergent network of conversations. And that's really what we're proclaiming here.
Mm-hmm.
Right? Just like a country is proclaimed out of nothing. You can draw this giant millions of square kilometers on a map, and I just proclaim this a country, boom, right? We are proclaiming the network of conversations, and we believe that this is the planetary brain that we need to actually do collective sense making on exactly what you're saying, get the message, and then do the calculations. What do we need to do in terms of governance? What do we need to do in terms of finance? What do we need to do in terms of the nonprofit sector? What do we need to do in terms of the religious sector? You know, how do we plug this into Pope Francis's latest encyclical that 1 billion people are supposedly supposed to be following, right?
Yep.
And say, hey, here's the implementation of the encyclical. You cool the planet, and that's how you save Mother Earth, which is the whole point of his encyclical. Anyway, facet after facet after facet of the hyperobject, we need collective sense making so that we can actually do this. And time's running out. So that's my plug for all of us coming together, hanging together. We're going to be here every Thursday. Yay.
Great.
A press conference every Thursday. So feel free to come by and just do literally like a 2-minute update.
Okay. Well, we will try.
Well, I mean, that's how we're doing for most of our time here is 2-minute updates and 2-minute debuts of conversations that are important, like this one. You guys got a full hour because yours is the most urgent, and we got to do it. All right. It's as simple as that. So anyway, please come back anytime you want. Guy, Yay, everyone, for 2-minute updates. It only takes 2 minutes. Literally, you come in here, here's my update. Bye, everybody. And so that's what we're going to continue on next. But first, let's give people a chance to, I don't know, do people want to ask questions? I know there's some people who need to present fairly soon because they've got things, but let's take a few minutes anyway for Q&A if that works for everybody. Yay? How does that work for you?
Yeah, sure. We can take a few minutes, but maybe also Guy should probably join. I think the question might be addressed to both of us.
Absolutely, because we need to take the holistic view. Okay, Dr. Don Pett has a question. Go for it, Don.
Yeah, thank you. I appreciate your comments and very scholarly and very clear explanation. My question is, you did not include in the great dangers the nuclear issue. That could happen any moment, and the experts are saying we have less than 10 years to get our act together. And I'm more of a behavioral scientist, you might say.
Mm-hmm.
So we find that nuclear weapons cause no pain. And the same thing with global warming, it doesn't cause a lot of pain until it's much too late. The COVID crisis causes a lot of pain. So we say that pleasure leads to change, leads to the same behavior, but pain leads to change. So it seems to me until we can change the way people think, they're going to continue to ignore, as we've done, the issue of global warming, as we've ignored. No one seems to have any solution that I'm aware of for the issue of nukes. There's no practical solution available. And I'm wondering what you're saying is, do you feel that's practical in terms of people's attitudes and willingness to respond?
I think I would first let Guy speak because he has a much better understanding of the nuclear issue.
One predicament at a time, please. There are a lot of things over which we have no control at all. One of the things that Dr. Tao's project takes on is the very thing over which we might have some control, which is cooling the planet. We don't have much control over how high-ranking government officials act and when and whether they're going to launch nuclear weapons at each other. There's a lot of things beyond our control. So I'm trying to focus on something over which we might have some control, thus Dr. Tao's project.
Yeah, I completely agree. So Gaia has been repeatedly criticized by some mainstream academics for being alarmist and for providing timelines that seems perhaps a little bit shorter than what linear projections of many models seems to indicate. But that's basically ignoring the nonlinear aspects of universe, including unpredictability of human societies and how we react and how things can escalate quickly beyond linear response. So I think what's the most important like attribute or skill a scientist or investigator can have, I think, is intuition. Even more than just quantitative accuracy on particular subject. And I think Dr. McPherson has some of the most impressive intuition that I have encountered in my career. So exactly, there are multiple threats, and there's no guarantee that any of these solutions will even be implemented or attempted. But it doesn't stop us from trying, because until we try it, we cannot say for certain that it won't work or ever be implemented.
We seem to be intent upon ignoring the precautionary principle and taking us always right to the brink. That seems to be the societal endeavor and has been for years. So if I seem alarmist, it's because I believe the situation is alarming. And continuing to ignore the precautionary principle and insisting that we take us right to the existential brink before we decide we have a problem is not really an appropriate strategy.
Mm-hmm.
I have a question. Thank you very much for your presentation, both of you. I may have missed it, but you may have said a timeline for getting these mirrors up enough to do the work you want to do, or if one mirror is enough. And I bring up timelines also because, and you may know a lot about this, Dr. McPherson, about the World Wildlife Fund's keeping track of populations of animals since 1970 and its downward curve headed for 0 large mammals by 2026. So that's just 5 years away. And in 5 years, trees don't get to their maximum, but, just by not mowing, we can do a lot. And if we, since 37% of our land on Earth is used for animal agriculture, if we let that go, like tomorrow, if people start going vegan, if people stopped eating animals, it would immediately have some cutting down of the trees, and the methane would stop and people would start reproducing, stop animals. So I'm very interested in what you know about that, and then how do the timelines compare? And I'm wanting to do as much as we can on both ends because I see the criticalness of it. Thank you.
Mm-hmm.
The biggest concern with the latest reports from World Wildlife Fund is that we're large mammals too. If there are no large mammals by 2026, that includes the large mammals known as Homo sapiens. Dr. Tao, can you fix this for us?
All right, so the questions, I think the main question is whether stopping animal agriculture can be a significant contributor to slowing down the further demise of the large mammals. So to answer that question, we need to really think quantitatively and assume that everybody on Earth turned vegan instantaneously today. We can probably reduce global CO2 emissions by roughly 10%. 10% is not in the order of magnitude that's sufficient to prevent a detectable change in the current trajectory. So it's not an effort that will actually have significant impact. People's energy and emotions would be much better spent, one, thinking we will help, of course, think quantitatively why that's the case, and really try to ditch just for a second our natural attachment to trees and nature, but really realize that regardless of how beautiful they are, they're pretty inefficient energy conversion devices. So the efficiency of photosynthesis is roughly like 1 or 2%, whereas our typical solar panels are like 20%. So the reason why we managed to destroy our planet so thoroughly is because of the efficiency of technology. It's difficult to imagine using nature. It's finely tuned, but it's inefficient. It's already too late to rely on the inefficiency of natural methods to tackle a problem caused by very efficient destruction machineries. So we really need to deploy the most efficient of our machineries to counter that effect. So once again, going vegan will have no measurable effect on the climate for the next decades.
Have you read Dr. James and Dr. Silas Rao's paper on sequestering 265 gigatons? They did a model.
Yes, there are many models out there, but the scientific overwhelming consensus is that, well, you can imagine 200-something gigatons, that's the emissions of only a few years, but the time scale required for, say, a forest to mature is on the order of 40 years. But compare a young forest and an old forest. They both have very green leaves. And that's not a good thing, because green leaves really absorb all the light. So even before they have filtered the air, they already exert their full heating power, extra heating power on planet Earth. So for the first 2-3 decades, there's a net detriment to planting new forest. So what we need to do, obviously it's important to keep biodiversity. And the best way to do that is to stop expanding land agriculture, leave what remains of our forest the way they are. Let's move agriculture to the oceans. Why to the oceans? So, well, now I'm trying to basically move my project to, say, institutions like MIT. And the reason I think MIT is a good place is they have a fantastic engineering department focusing on ocean technologies. And there are people starting to think about mariculture, just growing stuff in the really deep oceans. That's because we have such huge expanse of surface area over there. We have abundant sunlight over there. And it's not in the way of land mammals. So let's just leave what remains of our forest and let mammals reproduce. But there's no real benefit to promoting further forest growth, because at the current level of temperature extremes and the drought, it's simply not possible to keep them alive without significant energy investment to irrigation, which would further lead to CO2 emissions in the process. So it's really lost causes and really huge drains in finances and energies to look at natural solutions. These are certainly, I fully understand people's attachment to nature. And it really gives them a sense of hope and a sense of purpose. But
I like the sense of hope and purpose, but I also want to be factual. And I'm glad to hear that you've looked into it. I'm very curious about following up on that. You know, with only 9% of the land being forest right now, it's hard to picture, and 9 billion animals being killed every year. You know, that's not acceptable any way you look at it. But in terms of sequestering enough carbon and stopping all that, I really appreciate your comments. Thank you.
yes, I really agree that, you know, from ethical point of view, there's a point to be made about animal husbandry, but from a climate point of view, it doesn't really agree with facts and just the basic physical physics.
I would like to jump in just because I heard something you say that kind of raised the hairs on my neck, is somehow that our attachment to nature is sentimental or emotional or not efficient, and that to me illustrates a delusion of separation from nature, in that we have to regenerate the earth. We have to give back. We can't, from my thinking as an earth-based human, water-based human, we are water. And without water, if we don't get our relationship to water correct, then nothing we do matters. It doesn't matter whether we put ping pong balls in the ocean or panels in the sky. If we don't get our relationship to water correct, then we might as well be singing our swan song, because we can't detach ourselves from nature. That's one of the biggest problems that we have, is thinking that we can detach ourselves from nature. And so I have to put that out. No water, no nature. No water, no technology. No water, right? And so unless we can switch our perspective and work on that delusion of separation that we're all under, to one degree or another, all of us, it doesn't matter whether we eat meat or vegetables. It matters to some degree, but if we don't start seeing our planet as one life, an interconnected, interdependent, interwoven system, and realizing that the source of that is our water in relationship to our sun, then we're still just putting Band-Aids on something that is a gaping wound, right? As we're putting little small Band-Aids on something that will continue to bleed and bleed and bleed, no matter what technology we throw at it. And so really science can help us get there, but the shift that we have to make on this planet is not scientific. It is from the inside, it's cellular. It's our own relationship to our own water inside of our own self, and recognizing that where we stand, everything we see is an expression of water. And until we come into relationship, sacred relationship with water, it doesn't matter what ceremony we do, it's that covenant with water, then we're not going to be able to fix what Guy says, that we've taken ourselves to the edge. And that's the core thing that we have to do, is come back into correct relationship with our source, which is water here on earth. So that's my 2 bit. I loved everything you presented, but I keep hearing that, somehow we can fix this without correcting the core problem, which is our bad behavior on the earth. We can't expect to not change that core dysfunction and expect to fix things.
I have very good news. As we've known for decades, a warmer planet is a wetter planet, so there's more water coming our way.
And what happens if we destroy our atmosphere and do we lose water if the atmosphere thins? Are we losing water?
Can I answer the comment? I think I'm 100% in agreement with the fact that it's the inner work and a transition of consciousness that's the true start of solutions. And the reason why, say, people like Guy and I are doing this work is not for profit or fame or for scientific discoveries. It's out of just love for humanity, for the wonders that we're capable of achieving, and for the beauty of this world. And water, we want to fix the water cycle. The problem is on the current trajectory, and right now, the water cycle is broken because warmer temperatures drive faster evaporation and more intense floods. And that's destroying our forests, our ecosystems, and coastlines. What we want to do is to help nature restore its water cycle and balance. And that's where MEERs come in. We do not pretend that we are smarter than nature. We are students of nature. Before we even make any hypothesis or think of any stupid idea, most of the time, we go to hundreds of scientific papers, digging through knowledge accumulated by past generations of scientists on whose shoulder we stand, and to make incremental, tiny advances. So just to summarize, I think both Guy and I are in complete agreement that it's the heart and really where the work begins. And the transition on global level, hopefully, of the civilization to one of love and pursuit of inner work and peace, instead of like trappings of success and just consumerism, is where how we can eventually solve those. The engineering intervention, it's a test for us. It's a test of whether humanity has the capability to act in concert for a potentially sustainable future. No guarantees, right? But if we fail, then the answer is obvious. Then that's end of that. And it just, then we have to, follow, again, Guy's advice and live every day as it's the last day and live life fully. So thanks, Elizabeth. It's you're 100% correct.
Yeah, I good to see you, and Guy, so grateful you're here, and thank you for your beautiful presentations. I always hear something new every time I hear your presentations. And I just wanted to ask you, it's kind of a statement or a suggestion and also a question. As we know, a lot of forests are still being cut, and you talked about maintaining forests, but we know the Amazon's being cut down at a terrible rate. Here in the Pacific Northwest, forests are being decimated. We still have logging. And I see this as on two scales. There's the big scale, which you are talking about. Let's cool the planet. But I think there's also a small scale, which I think maybe is more what Elizabeth or I would be talking about, which is a kind of helping people also get connected back to nature and a different way of living and impacting the planet. So that could be planting trees, for example. It could be not mowing the lawn. So I think there's these small things, small gestures that people can make that won't necessarily save the climate, right? But that will help us come back into a sane relationship with nature and help us grow and transform spiritually as well as, physically. And then, yes, we also need to find a way to help your project get financed and for people to know about it so that that can happen, to give us maybe some kind of chance for cooling the planet for the future and let Mother Earth do her work. Thank you.
I just wanted to say in 4 minutes, we're going to have to shift gears because there's some folks who need to present before the top of the hour. It's 2 a.m. for some of the folks here. So for the last 4 minutes, I want to yield to Guy and Ye, our guests of honor. Let them have the final words, and then we're going to shift gears. Guy and Ye, feel free to stick around. We're going to have a lot more presentations and then an after party until the wee hours of the morning. So feel free to stick around and come and go as you please. With that, let's give a warm thanks and much gratitude and love to Guy and Ye. And let's give them a big warm welcome home because we need you here. right? We need you and you need us, right? We're here pioneering collective superintelligence through the network of conversations, press conference, snack bar, Togetherland, and open houses, and so many other mechanisms. We're creating the mechanics of collective superintelligence. So we need each other. Please keep coming back with that. I'm going to go on mute. Guy, yay, the last words. Take your time, 3 or 4 minutes.
I just want to point out very briefly that there's no magic bullet here. There's no super solution. And the MEER's ReflEction project is a significant step towards stabilizing planetary temperature. But Dr. Tao will never say that it's all we need to do. I think it's a critically important first step. If you know any billionaire or have any 7 degrees of connection away from a billionaire, please, we need to get this MEER's ReflEction project underway, start conducting more research and implementing what we do know no later than last week. This is imperative. And it's just a start. And I'm sure Dr. Tao would be willing to address that very notion that it's just a start. And what comes next involves all of us changing our behavior and acting in a way that demonstrates that we actually care about the living planet. That's my final words. Thank you. Please, Dr. Tao, take over.
Yes, guys, exactly right. That it's just the first baby step, perhaps in some direction, in the general direction of a potential solution. And so there's many battles to be fought. There's the sharing the knowledge with everybody. And for that, I rely on, and we rely on all of you to share this video and also tell your loved ones about perhaps there's an alternative way to look at the problem rather than just being fixated on trying to kill the fossil fuel industries because time is running out. And like for somebody working in the field like myself, there's also a lot of work educating colleagues about the urgency and then trying to recruit more engineers to this climate problem. So this year I've spent just giving similar talks to the engineering community. And for the climate mitigation community, geoengineering has somehow become synonymous to stratospheric aerosol injection, which carries a lot of problems. Basically, if we were to start such a thing, then we'll be blocking out more and more of the sky from ecosystems. So the light level will continue to dwindle because it's basically encouraging continued consumption of fossil fuel without worrying about, in the short term, temperature problems. So in the climate engineering community, we are also spending a lot of time just communicating with the different teams and trying to talk about each other's projects. So arriving at consensus on the solution front is also, will take time. But if you guys can help with getting financing and also publicizing the project, that would help not only our project specifically, but the whole community of engineers and scientists to have more open discussions and more public discussions about the various options we have in order for the world to make the best educated decision, hopefully not beyond next year, because if we don't get a full implementation started in 10 years, then I personally don't see much probability remaining for sustainability. So again, thanks for Jamin for organizing this and for his perseverance, and for all of you to listening to me. And thanks for Guy for his leadership in bringing the urgency of the issue to the attention of the world against criticism that seems to be across the board, except for people who really looked into the matter or who do not have vested interest. So, so thank you, Guy, and thank you, Jamin, and everybody.